Welcome to another video in the Sunrise series, showcasing the outcomes of Use Case 3.1, Highway Automated Driving Validation, Map-Based Perception and Decision-Making. In this video, we apply the Sunrise SAF for safety assurance of a map-based CCAM system to verify that it plans safe paths using HD map data. 5 parts of the SAF will be demonstrated, namely concretize, execute, test, evaluate, coverage, and the safety case building. The test case setup is based on simulations carried out in IPG CarMaker. The system under test is a highway autopilot with electronic horizon map data. There are 2 test scenarios. UC3.1-A studies adaptation to speed limits. UC3.1-B studies speed choice and lane keeping in curves. The safety goals are: for lateral control, the vehicle must stay within its lane. For longitudinal control, the system should use deceleration values typical of human drivers to avoid rear-end collision risks, with acceptable undershoot and overshoot speeds. In curves, the speed must be similar to human speed for comfort considerations. See Section 6 of D3.4. We followed a safety argumentation checklist that covered a microscopic evaluation of results for individual scenarios, a macroscopic evaluation by aggregating the results into comprehensive charts. Key artifacts include coverage of the scenario space with comprehensive charts and determination of internal and boundary points. See Section 4.1 of D3.4, and the evaluation of compatibility with human-driven vehicles. We will show these steps. Concretize. There are 2 logical scenarios defined by querying safety pool and revised by experts. UC3.1-A has 3 parameters and was sampled with 5,000 random points. UC3.1-B has 5 parameters and was sampled with 622 random points. Execute. The concrete scenarios are simulated in IPG CarMaker. Test, evaluate. The longitudinal velocity, velocity undershoot and overshoot, longitudinal and lateral acceleration, and distance from lane edges were recorded. Coverage. The individual metrics above were aggregated into diagrams that spanned the entire logical scenario space. Safety case. The maximum deceleration and velocity undershoot in speed adaptation were assessed. They are conditionally acceptable. Safety case. The lateral clearance with lane edges test was passed. Safety case. The accelerations and the speed choice in curves are human compatible. There are 2 logical scenarios, one for each sub-use case. Initially, they were defined by querying safety pool and were slightly revised by experts. For UC3.1-A, the logical scenario has 3 parameters as follows. This was sampled with 5,000 random concrete scenarios. For UC3.1-B, the logical scenario involves 2 curves in opposite directions, with the inversion of curvature challenging the system. It has 6 parameters, of which the last is constant. This was sampled with 622 random concrete scenarios. Execute. The simulations were executed in CarMaker, using half a day on a desktop computer. Test, evaluate. The complete logs were recorded and post-processed, extracting the longitudinal velocity, longitudinal and lateral accelerations, speed in curves, and lateral distance from the lane edges. Coverage. The individual metrics above were aggregated into diagrams that spanned the entire logical scenario space. Boundary points and points inside the safe subspace are identified, according to the method in D3.4 Section 4.1. Simulation results for UC3.1-A show deceleration needs for speed limit adaptation based on distance and velocity variations. The CCAM system's performance across the entire logical scenario is shown in a chart, with concrete scenarios marked with dots. The safety argument here suggests that if the speed limit decreases by 20 km per hour steps, detected at least 100 meters ahead on the map, red dashed box, then deceleration happens well within the blue zone, and the boundary at -4 meters per square second, which could signify a dangerous deceleration, is far away. All realistic scenarios with a speed reduction of less than 20 km per hour fall within the safe region. CD 3.4 Section 4.1. So there's no need for extra sampling to precisely identify the boundary. Concerning the velocity undershoot, which might penalize traffic flow, D3.4 Section 6. The following chart summarizes the findings. It shows the contour plots of velocity undershoot. Hard brakes, on the right, can cause significant undershoot, negatively impacting traffic flow. When the speed reduction is minor, the overshoot remains under 5 km per hour, shown in the blue region. Simulation results for UC3.1-B are summarized in the following charts. The charts show the lateral distances from the left and right edges plotted against the curvature of the first curve, x-axis, and the second curve, y-axis. The most critical conditions arise when the curvature sign changes with little impact from the curve radius. The system maintains a minimum clearance of 0.39 m within the lane. Regarding the selection of speed in curves, the following chart compares the lateral acceleration to the average human choice, left, and displays the GG diagram that indicates accelerations within the human naturalistic range, right? In this video, we have shown expert refined logical scenario. Test results are aggregated into charts covering the entire logical scenario. The application domain happens to be well within the safe scenario subregion. No need for further sampling. Human-compatible maneuvers. Concerning limitations and future work, the following comments apply. Users might wish to set different acceptance thresholds, which might need refining the sampling, e.g., deceleration limited to -1 meters per square second. Adaptive lateral clearance. Better match with human speed choice in the curve. So far, the CCAM system is slower.